Welcome everyone. Today in this video we are going to see more access methods which are implemented in the MAC layer. In the last video we saw how CSMA-CD fails to work in the wireless media. There are different problems which are observed in the wireless media such as hidden terminal problem or exposed terminal problem, and there is a near far problem. So CSMA-CD may work well in the fixed networks, but it does not work well in the wireless media or wireless networks. So for mobile computation or mobile communication, CSMA-CD is not a feasible solution. But apart from CSMA-CD, there are several other methods which can be used for accessing the media. So let's look at those methods in very brief, because these methods are not part of our syllabus. Our focus is on providing solutions to implementation of CSMA-CD in the wireless media. So what are the other different medium access methods? Some of them we have already studied previously, like SDMA, space division multiple access, where we segment the space into different geographical regions. That is, one large geographical region is divided into smaller regions, and we use different directed antennas to cover each region, so different users can access the medium separately using the same frequency channel also. Okay, so that is observed in the cell structure. GSM, we have seen SDMA is implemented. It is rarely implemented alone. It is always implemented in conjunction with either TDMA or FDMA, or sometimes both also. Okay, then next one is a frequency division multiple access, FDMA, in which we already saw that entire bandwidth will be divided into smaller bandwidths, and each user may be given a different bandwidth, small bandwidth, for communication. So that avoids the collision, as well as that avoids the interference from each other. But the drawback of this FDMA is we have very limited frequency resources, that is frequency channels, so all users cannot be satisfied with this scheme. So then, to avoid this, there is another solution, that is TDMA, time division multiple access, where everyone can access the bandwidth, but not at the same time, at different times, that is at different time slots. So entire bandwidth is available for only small amount of time. So again, it has a drawback that if anyone wants to access the medium for larger time, what it should do. So each of these methods has certain drawbacks, certain advantages, but these are very basic multiple access methods or medium access methods. Then the ones that we have not seen previously, let's see them one right now. You might have studied about Aloha scheme. Aloha means hello, which is primarily used for accessing the medium in certain scenarios or fixed networks. There are two forms. One is pure Aloha, or it is called as classical Aloha, and then there is a slotted Aloha. What Aloha does is that in pure Aloha, if user has a data to transmit, it immediately starts transmitting it. So it doesn't wait to see whether medium is free or it is occupied by someone or anything else. So whenever a user has a data, it randomly starts transmitting. Okay, that is completely contrasting to carrier sense multiple access. Advantage of this is very simple in nature. There is no coordination required, that is no coordination provided rather than required. That is, there is no administrator that who is transmitting when. So chances of collision are more in the pure Aloha or classical Aloha. Okay, so but still it is very simple to implement and provides a good efficiency under light load conditions. That means if number of users are very less, this scheme works very well. So you don't have to invest so much in implementation of this scheme. So about 18% of channel efficiency is observed using pure Aloha, which is very low actually. Now by channel efficiency, what do we mean? Let's suppose a channel is available for 24 hours. Only 4 to 5 hours the channel will be utilized by the users. For remaining hours, channel remains unutilized, and that's why it is wasted. So how to increase this channel efficiency, or how to avoid this wastage of a channel? For that, and to avoid the collisions which are observed in the pure Aloha or classical Aloha, they modified it to slotted Aloha, where whenever a user has a data to transmit, it cannot directly start transmitting. It has to wait for beginning of a certain time slot. So entire time period will be divided into time slots, and if you have a data to transmit, you can begin transmitting it only at the beginning of each time slot. So up to certain extent collision can be avoided, but not entirely it can be avoided, and it also improves the channel efficiency up to 36%. So these are Aloha schemes. Then to avoid the collisions and to drastically improve the channel efficiency, one more advanced technique was designed, that was demand assigned multiple access. That means whenever you need a channel for transmission, you have to demand it from somewhere, and that will be your administrator. It contains basically three techniques. First one is explicit reservation, second is implicit reservation, and third one is a reservation TDMA. In explicit reservation, which is also called as reservation Aloha, there are basically two phases. First one is a contention phase and second one is a reservation phase. What happens in this case is that during contention phase, you cannot transmit your data. You have to reserve the time slots in which you will transmit the data. Okay, so in the contention phase, all users will compete with each other to reserve time slots. No data transmission is possible. Okay, so contention phase, in contention phase there will be a competition between users for reserving the time slot. Okay, once this competition is over, that is contention phase is over, you can start the reservation phase, or administrator starts the reservation phase, in which depending on the results of this contention, each user is allocated some time slots for transmission of data. So collision is avoided during data transmission because each user will have a reserved time slot, so no two users will start transmitting at the same time. Each user will transmit only in its allocated time slot. But collision can be possible in the contention phase. Suppose users are competing for reserving a time slot and two users demand same time slots or different time slot at the same time. Suppose this is your contention phase. Now two users demand for same time slot for reserving the future data transmission time slots. Then collision is possible. So one of the user will get chance to transmit, other will be deprived of transmission of a data. So although collision is avoided during a transmission of data, collision can happen during the contention phase also. So, but it is still better than pure or slotted Aloha. Then there is an implicit reservation phase, that is called as PRMA, Packet Reservation Multiple Access. Now in this one, users do not compete with each other for reservation of time slot. This method also contains contention phase and reservation phase, but during contention phase, users do not compete with each other, rather base station assigns the reservation. Okay, base station during the contention phase will assign the reservation to all users. If number of users are less compared to the contention time slots, then remaining slots will be kept free. and during those free time slots, same users can compete with each other for access to the time slot. Again, similar to explicit reservation, during reservation phase, each user can transmit its data according to allocated time slot decided by the administrator, and collision is avoided. Okay, again, collision is possible in the contention phase, but up to very reduced extent, because number of free time slots will be very less. Then final method of DAMA, that is demand assignment multiple access, is that reservation DMA, where again there will be contention phase and reservation phase, but there will be n mini slots and you can reserve k data slots. That means during n mini slots, each user can occupy one mini slot, where each user will reserve number of data slots. So it's not limited that one user will get only one data slot for transmission. Okay, so this helps not only in reducing collision but also increasing the channel efficiency. So all of these three sub methods of DMA can achieve channel efficiency up to 80%, which is much more larger than the Aloha schemes, normal Aloha or pure Aloha or slotted Aloha. So these are different medium access methods, but all these methods are not providing the solution to our original problem, that is hidden, exposed and near or far terminal problems. Apart from that, this DMA is not as flexible as Aloha scheme. That means you have a fixed time slot. So let's say I have been allocated 3 slots. My transmission gets completed during 2 slots. Again, 1 slots remain free. So that is not flexible to assign this slot to any other user. Then next problem is, what if there is no base station or no administrator? Then who is going to decide allocation of time slots? So all these problems lead to only one answer: how to implement medium access protocol in wireless media. Every medium access method which is described in fixed networks has certain drawback and doesn't solve the problem of hidden, exposed, near and far terminal. Okay, so there is a simple solution which is a part of our syllabus provided to all these problems. Is a new method. It's called as multiple access with collision avoidance, abbreviated as MACA. Okay, now it is very simple solution. There are several advances happened in this particular method, but let's get introduced to this MACA. What MACA does is that it uses short signaling packets for avoiding the collisions during transmission of a data. So rather than contention phase, there will be signaling packets utilized for accessing the media. That means no contention phase. Whenever you have a data to transmit, first you have to send these signaling packets to avoid the collision, and during the transmission of data, there is a very minimum possibility that collision will occur. Okay, so which are these signaling packets? There are 2 signaling packets. One is named as RTS, that is request to send, and other is CTS, which is clear to send. RTS packet is sent by a transmitter for requesting the right to send from a receiver. That means if there is a transmitter, if there is a transmitter and there is a receiver, and transmitter wants to send a data to receiver, it will not directly start sending the data. First it will transmit RTS, and it will request receiver whether it can send a data or not. If receiver is free and ready to accept any data transmission, then it will reply with another signaling packet that is called as CTS. Okay, so RTS and CTS is like a handshaking process which is performed before transmission of actual data. So what are the contents of these signaling packets RTS and CTS? So RTS and CTS contain simple information like who is the sender, that is sender address, what is the receiver address, and what is the size of packet, that is data of packet that it wants to transmit. So receiver address is included because this RTS is a broadcast packet. Okay, it will be broadcasted to all the stations within the network. Now a receiver identifies his own address and responds with the CTS. Okay, this method solves the hidden and exposed terminal problems. How? Let's see that. So let's see first the hidden terminal problem. How MACA or MSCA avoids the problem of hidden terminals. Now consider the scenario, that is first diagram, this one, where there are three stations A, B and C. A and C both want to send the data to B, similar to the problem that we have seen the explanation of hidden terminal problem. Now in this case, when we are implementing MSCA, they both will not start transmitting the data simultaneously. Rather than that, what they will do, first A sends the RTS to B. Now if B is free, it will send a CTS to A. Now although A is sending an RTS, which is a broadcast packet, since C is out of coverage area of the A, C will not receive the RTS. C will receive only CTS, which is responded by the B. CTS is also a broadcast packet. Okay, now once C receives the CTS, it gets to know that B is busy in the communication. So C defers the transmission of RTS to B. Okay, another scenario, when A and C both send the RTS at the same time. Now it is up to B to respond which terminal, that is either A or C, can transmit the data that is mentioned in the CTS. So let's assume that A and C both are sending the RTS at the same time. Now B decides that A can transmit the data. So in the CTS, it will mention sender's address as address of A. Now same CTS is received by C. C sees that the sender's address is mentioned which is not of an address of C. So C will not transmit. So this is how it avoids the hidden terminal problem and in turn avoids the collision at the B. Okay, so this is how hidden terminal problem is solved. Now what about exposed terminal problem, where there is a fourth terminal D. Now in the exposed terminal we saw that B wants to send the data to A and C wants to send the data to D. Let's say here is a D and C wants to send the data to D. Now since we are using RTS and CTS, C does not have to wait for permission from B for transmission to D, because when B wants to send the data to A, B broadcast RTS packet. You can see RTS is given to A, RTS is given to C. But in this RTS packet, the receiver address is address of A. So C does not respond to B because address is of A. Now when C has to transmit the data to D, it checks that D is free because communication between B and A is going on and D is free. So C sends the RTS to D. Same RTS will be given to B. Now B realizes that the address mentioned in the RTS is not of its own, it is of D. So it does not respond to it. A responds to B via CTS and D responds to C via CTS. Now C and B both realizes that this communication is possible, so they can proceed further with the data transmission. So again, there is no chance of exposed terminal because both C and B can transmit at the same time because their receivers are different. So this is the simple scheme which is used by MACA for avoiding hidden and exposed terminal problem. Same scheme can be used for avoiding near and far terminal problem also, where each terminal can be each terminal can use RTS CTS, so that power control is not mandatory in case of near far problem. The one problem that is observed in the MACA, obviously every method has certain drawback, is overhead associated with the RTS and CTS transmission. So in usual access methods, we are transmitting only data. So if we have 90 packets to transmit, only 90 packets will be transmitted through the medium. But in case of RTS CTS, 2 additional packets will be involved in the communication. Those will be RTS and CTS. Okay, so that is called as transmitting 92 packets instead of 90. Okay, when number of packets are more, this overhead or this is additional packet is considered very less. But if you want to transmit only one packet to the receiver, for sending only one data packet to the receiver, you are transmitting 2 control packets to the receiver, and that is not desirable. So for short and time critical data packets, this is not negligible. Time critical, why? Because handshaking process requires certain time to conclude, and if you are transmitting videos which is a time critical data, then this overhead is not negligible. You can observe delays in the video reception. Okay, MACA also assumes that there is a symmetrical transmission and reception conditions. That means whatever condition the transmitter are using, same atmospheric and infrastructural conditions available at the receiver. So congestion control may be observed, but flow control may not be obtained using MACA. Okay, so this is about MACA. Let's see the state diagram for sender and receiver. As you can see, sender initially is in the idle state. Okay, when it has a data to transmit, it sends a RTS and enters into the wait for the sending, wait for the CTS. That is the second step. Once receiver, which is originally in the idle state, that is the first step. Once it receives the RTS, if it is free, it responds with the CTS and wait for data. So it goes into the second state, that is wait for data. So CTS is broadcasted. Now that CTS will be received by the sender. So it enters into the third stage, where after receiving a CTS, it transmits the data and stays in the wait state. Now why wait state? Because after sending the data, it will wait for the acknowledgement from the receiver whether data is received or not. Okay, now once receiver receives the data, it sends the acknowledgement or negative acknowledgement, whatever it is. Whether if data is not received within the specified time, it will send a negative acknowledgement. It goes into the idle state again. Okay, so once acknowledgement is received, again sender goes back into the idle state. If it receives negative acknowledgement, it goes back into the second stage, that is sender goes back into the second stage and retransmits the data. Okay, so this is how MACA works. It is very simple solution. It avoids the collisions, it avoids contention, it avoids use of central administrator or arbiter, so no additional infrastructure is required. Only small drawback is that additional packet overhead will be there in case of small data transmission. That's all for today. Thank you.